So in this code, we are going to discuss about image augmentation and CNN classification. So we load the fashion MNIST dataset. It contains around 60,000 grayscale images of clothing items across 10 different categories like shirts, trousers, bags, and sneakers. So each image is basically 28 cross 28 pixels, and we expand the channel dimension to match the input shape expected by our 2D layer. We also normalize the pixel values to range between 0 and 1, which is standard for neural networks. So here we can see the preview of the 12 images to understand the data distribution visually. So this gives us an intuitive feel of what our model will learn from this. So then we're gonna create the dataset pipelines, train DS for regular dataset, and test DS to test for evaluation. So these are shuffled, batched, and prefetched for performance using data.autotune feature. And then we're gonna define the augmentation pipeline. So we introduce the cut mix overlays one image onto other and blend their labels, which blends their labels, whereas the random flip mirrors images horizontally. This basically enhances diversity and especially for dataset with spatial or image sensitive patterns. We then map this function onto training dataset using train ds.map. We're gonna see the augmented images. Before training, we visualize how cut mix plus flip transforms images. You'll notice parts of one item cut and blended with other, making it training more challenging and rich. So this forces the model to learn more generalizable patterns rather than overfitting to exact shapes. And then we're gonna define a simple CNN architecture, which has a flattened layer, dense with 128 and ReLU, and dropout rate of zero point 0.3, and dense with 10 and softmax. It's lightweight yet good enough to evaluate augmentation effects. We're going to train the model on original data for 10 epochs, and after we save the training and validation metrics for comparison, and then we train the augmented model as well. So first we trained with no augmentation. After that we trained with augmentations for 10 epochs. Here we can see the validation accuracy plots. So this reveals whether the augmentation helps the model generation better on unseen data. So these are the test accuracy and with and no augmentation. With augmentation, which with no augmentation it is around 87. With augmentation it is a slight less. So here are the predictions. You can see that the true no augmentation and with augmented prediction. This is the training loss. So basically often training is noisier, but generalization generalizes better with augmentation. So we can see the prediction of the augmented model. So that's it about this image augmentation and CNN classification. Moving on to using fast AI augmentation. So basically, fast AI is one of the fastest ways to build and train deep learning models, especially for computer vision. In this code, we'll walk through a complete example of image classification using fast AI and the Oxford IIIT Wedge dataset, and automatic image augmentation like flipping, rotating, zooming, and warping. So first we install the FastAI library. So FastAI is basically built on top of PyTorch, and it provides conscious abstraction for rapid experimentation. It basically simplifies data loading, transformation, training, evaluation, and visualization. and then we gonna load the built-in data to download from the Oxford IIIT Pets dataset. So basically, this dataset includes over 7,000 images of 37 pet breeds. We'll use simple labeling. If the file name starts with capital letter, it's a cat. Otherwise, it's a dog. We verifying the labels with 10 file names and corresponding labels with using a data frame. We define the data block with so we define a data block with augmentation. We use the data block which tells the fast AI what the input is gonna be and output types. So with the transformations to apply, we resize all the images to 224 cross 224, and then apply augmentations, flip, zoom, rotate, light change, and wrap them. And then after that, we're gonna visualize the augmented data. So after building the model using ResNet 18 pre-trained, which is already pre-trained image net, we're gonna attach a head suitable for binary classification, cat vs dog, for our final predictions, and also use the cross entropy loss, and we're gonna track accuracy. So these are the prediction actual vs probability, and here the class distribution of number of cat images and dog images it has been trained on. Thank you.